These questions will be from rotational motion and conservation of momentum and all those topics. And the first question is that a uniform rod, which is stick of mass m and length L, lies horizontal with its end B on the edge of the table, that is a contact point. The other end A is held and suddenly released. At the instant immediately after release, the rod begins to rotate about point B. The contact point acts as an instantaneous pivot. The gravity acts at the center of mass located at a distance L by 2 from B. So based on this, we are having these 4 questions. And in these 4 questions, we are going to solve them about how it is first of all is about the torque, then it is angular acceleration, both are around B, and then it's a vertical acceleration on the center of the mass, and finally is part D, which is basically related with our C part. Find the vertical force on at B. So first of all, we are going to draw an approximate figure for the given question, and for that, suppose this is some kind of table, and on this table there is a stick, or we can say a stick is lying something like this, and it is given that the open point is called A, and the point which is contact with this table is called as B, and total length of the stick is given as L, and let us suppose there is its center of mass is point C. So entire its mg will be acting at this center of mass, and the length on the either side of center of mass will be over L by 2. And initially it is given that there is some support at A, and when this support is let go, this rod is going to pivot about this point A. And let us suppose there is a angular acceleration of alpha. So first part, it is talking about the torque around B, and let us try to understand what will be the forces, or we can say free body forces, at the instant after the release. So we can say free body forces, and these forces are instant after release. And obviously there will be mg acting in the downward direction, which we have already drawn. So we can say there will be a gravitational force, that is gravity, let us call that W, and which will be equal to mg, and it will be acting in the downward direction, okay, at center of mass, and that point we have called as C. And there will be also a reaction force that will be at B. So there will be reaction force at contact B, reaction force at contact B, and which we called as our R. And otherwise there is no other external forces acting on it except its own reaction as well as the weight. So let us sort it out for our part A. And so there will be torque about B, and the torque about B will be because of this mg. So you can say our torque about B is due to mg. So we can say that our torque at point B will be equal to the force which is our mg multiplied by the perpendicular distance, which is our L/2. And next is our part B. And part B, we are supposed to find out the angular acceleration about B. And in order to find out angular acceleration, first of all, we are required to find out the moment of inertia about its center of mass. So you can say moment of inertia of rod about its center of mass, which we can call as ICM, and that will be equal to 1/12 ml square. But the rod is going to pivot about our point B, so therefore we are going to use the parallel axis theorem and find out the moment of inertia about this point B. So we can say using parallel axis theorem, moment of inertia about B, which is suppose our IB, will be equal to moment of inertia about the center of mass of the body, and the distance between the two, which is our D. D here is L/2. And we substitute it, we get this as I of B. ICM is our 1.12 ml square, plus this comes as our ml square upon 4, which will be giving us 1/3 ml square. This is also a standard formula for our moment of inertia at any end of the rod. Now we can find out our angular acceleration, which is our final requirement. So we can say that our angular acceleration, and that angular acceleration will be because of the or before that, let's write down the rotational equation. Okay, that is going to help us because that is easy to relate. So you can say our rotational equation, which is nothing but our torque at point B, will be equal to moment of inertia at B, and that needs angular acceleration. Okay. Torque at B, we already know it, So we substitute, we get this as our ml mg L by 2, I of b is 1 by 3 ml square times the acceleration. And this mass and square goes away. Therefore, we get our angular acceleration will be equal to, it will be 3 by 2 g upon L. Okay, so this will be our angular acceleration. And in the part C, we are supposed to find out the vertical acceleration, and we assume that the vertical acceleration, which will be through center of mass, obviously it is in the downward direction, and it is our A. So we come to our part C. Part C, we are going to find out the linear acceleration of the center of mass. Okay. So in this case, it is a pure rotation about the fixed point B. Therefore, we can say that at any instant, it's a linear acceleration, or we can also call it as a, for a fraction of second, right after it is going to rotate, we can call that as a tangential acceleration of a point at a distance r, the pivot. Okay. So we can say that for pure rotation, about fixed point B, the instantaneous linear, or here for this particular case we can also call it a tangential acceleration of a point at a distance r from the pivot. Let us call this as acceleration as A tangential, which will be equal to r times the angular acceleration. So which basically means that if this is the rod and we have to suppose to find out the at certain point, and this point is at a distance r from the pivot point, which in this case is our B, and we know that its angular acceleration is alpha, and obviously as the rod is going to pivot about this point B, it is going to trace something like a circle. Therefore, the acceleration we can say will be somewhat tangential to this circle. And for a small instant, we can assume that it is dropping straight for a fraction of a second. That's why we call this as A10, or we can also call it as A. And in this particular question, this is our center of mass, so value of R is our L by 2. Okay. Therefore, we can say our acceleration of our center of mass will be equal to distance is our L by 2, and we have alpha is our angular acceleration, which we found out is our 3 by 2 g divided by L, and here L and L cancels out, so we get our acceleration of our center of mass will be equal to 3 by 4 times g, okay, obviously in the downward direction. So this was the C part. And in the D part, we are supposed to find out what will be the vertical force at B, which we have denoted as a reaction force. So we have a part D, and for that, because the motion is entirely in the vertical, so we are going to use that our summation of our vertical forces, okay, and we are going to find those summation. And in terms of Newton's law, we can call this as a translational Newton's second law for vertical motion. So we can say that for translational Newton's second law, and here it is only vertical motion, so we are going to write it for vertical motion. So vertical, let us say that it is entirely in y direction, therefore we can say that summation of the forces in y direction, and that will be equal to our m and acceleration of the center of mass in y direction. Okay. And for that we can just draw an approximate figure. So this is our B point, and here is our R, and if we take the coordinate axis, this is our x and we have a y, and the another force which will be acting vertically will be our in the downward direction, that is our mg. So we can take R as positive and y in mg, that will be our negative because it is acting downward direction. Okay. So we can say that so forces will be equal to our net force in y direction, that will be our, this reaction is nothing but our normal, that is our n minus mg, and that we can write will be equal to our mass m, and we found out it is 3/4 times g, and it will be also in downward direction, so it will be also our negative, and we are interested in finding out the normal. So we can say our normal will be equal to, this comes as our mg minus 3/4 times mg, so which gives us that the normal will be equal to 1/4 times mg. So this is our, and its direction will be in upward direction. Okay. Rest of the all the things are in the downward except this normal. So this was our part D and the first question. We come to the next question, and it states that a particle of mass m is attached to a vertical post of radius r by a light inextensible string. Initially, the particle is at a distance r from the center of the post and moves in a horizontal plane with a tangential speed v0. And so in this case, there are two different situations. The two different situations are considered. The string passes through the small smooth hole located at the top of the post and at its center, the string is gradually shortened by pulling it downward through the hole. And in the second part, the string is wound around the outside of the post as the particle moves, so that the length of the free portion of the string decreases as it wraps around the post. So based on both cases, for each case we have two questions. Identify the physical quantity that remain conserved during the motion, and second part, determine the final speed of the particle when it reaches the surface of the post, that is, when it is at a distance from the center becomes equal to r. So here it is given two situations. In the first situation, we are said that there is a vertical post. Suppose this is our vertical post, and there is a small hole along the length of this post, and through this small hole there is a thread, and to which we have attached a mass, that is our m, and this thread is passed through the hole and we take out from the bottom. So in this case we are gently pulling this, you can say, thread through this hole, so that this mass come closer and closer to our rod. Okay. And r is given as the radius of this. So we have to find out the speed when the mass reaches the radius at the point r. So this is the basic first part rather. Okay. So in this case, let me draw this. Let us call this as point as O. Okay, and this is our M. So this is our point O, and this is our other point, which is mass M, and there will be tension in the string, and that tension in the string is our T. Okay, and it is acting radially to the center of the post. Okay. And first of all, we can easily find out the torque, okay, and then we can move about the momentum, and basically it is conservation of the momentum. And we are going to start with because in the first case it is said that identify the quantities that remain conserved during the motion, and also it will be you can say rotating in like a circle, something like this, and its velocity is said to be given as v0, tangential velocity. So its velocity over v0 is given to us. Okay, so it is rotating, as well as we are pulling the string downward through this hole, and the string is getting shortened. Okay. And at some point this string will be at a distance r from this O. That is our actual question which we are supposed to find out. So like we said, there is a tension T acting radially inward toward the center. So we have tension T acts radially inward, and that is toward the center of the post. Center of the post. Okay. And so obviously this will be, we can say this makes the force is tension, which we can also call it as a central force. And next we are going to determine the torque as well as the angular momentum, which will be because of the conservation. So let us assume that torque about the center that is our tau is given as R cross F, and this R in this case is the position vector of the mass from the center. So you can say R is the position vector of mass M and this force is also our parallel to R. So both this R and force will be radial. So we can write that our F is parallel to R, or we can say both are radial. And if both are radial, therefore we can say that our torque, the cross product, will be equal to 0. So which basically means there is no external torque about the center. So we can say no external torque about the center. So in case of this string, this force is nothing but our tension. Okay, so this is our force F, and like I said, this R is the position vector of the mass. Okay, so both are radial in direction, or we can say parallel with each other. So therefore we can write that by the principle of conservation of momentum, because there is no external force, the angular momentum about the center will be conserved all the times, because there is no force acting, external force rather. Therefore we can say that the angular momentum let us call this as our L about the center is conserved all the time. And we can also write that this our angular momentum, that's our L, will be equal to our mass, and we can call this as let us call this a distance as R, because R is our initial distance. Let us call this as radial distance as rho. Okay, at any rho radial distance, and that will be equal to V perpendicular. Okay. So here rho is our radial distance, at any given time, and this V perpendicular, it is the component of velocity perpendicular to this rho. component of velocity perpendicular to rho. So it means that our motion is tangential because it is moving in inward direction initially, and force is central. Okay, so therefore the path is it is going to generate a spiral inward path. So which basically means that there will be two kind of forces acting on this mass m. One will be the tension force, that will be because we are pulling the thread in the downward direction, and other one is in a spiral motion. So ultimately we are going to get, you can say, the motion will be spiral inward. Therefore we can say that since the motion is tangential initially and force is central. Force is central. Therefore we can say that the path is spiral inward. The path is spiral inward. So spiral inward basically means that suppose this is our initial position of the mass and this is a thread, we are pulling it. So it is going to make, let me make a shorter one. So it is going to make this circle and it is going to make a spiral, something like this. Okay, it will be moving in this direction because it is moving, having two motion. One is moving a circle and then is a force on the string that is acting in the downward direction. And so like we said that the velocity, if it's moving with the velocity of v naught, that will be perpendicular to our rho, which we called it as a at any moment a distance, that is this is our rho. Therefore we can say that our velocity remains perpendicular to our rho, that is our distance. So we can find out the angular momentum initially when it is at a distance of r from the center. So we can say our initial angular momentum, that is of L of I, which is equal to our m multiplied by r, and its velocity is v naught. And at any radial distance, let us suppose its velocity is v, and we can say that at a radial distance, which we have considered rho, and the angular momentum, that is where L will be equal to m rho times v. Okay. And according to conservation, of angular momentum, we can write our Li is equal to our L. Let us call this as L rho. Therefore we can say that our mr v naught will be equal to m rho times v, and we can write this mass and mass cancels out, so we get that V will be equal to V naught, and we have this is R upon rho. So this is our velocity part, and we have to find out that at point at rho is equal to capital R, we are supposed to find out the velocity, and we are simply going to substitute. So we can say our velocity at a distance R will be equal to V naught R upon capital R. So this is our velocity at as soon as it is going to hit the post. And we come to our case B. And in case B, we can just draw the figure. So this is our post, and in this case the string is wound around the post. So it is going to wound something like this. So it is going to wound up like a thread on a post. And so in this case, if we look closely, we can just draw this particular figure from the top side also, and that will make it more clear. So from the top side, we can clearly see that it is going to as a circle, and R is the radius, and it will look like that this thread is just touching the circle. So this will be the position of the thread. Okay. And this is mass m, and it is going to rotate in this direction so that it is able to wound, and that velocity is given as our V naught, and the tension will be in this direction now. Okay. And if we complete the triangle, so this will be our all the forces that will be acting on this. So this is a major difference between the two, in part A as well as in part B. Okay. And so in this case, the string is not going to pass through the hole, which is our denoted as O, but it is going to wrap around the exterior of the cylinder as the mass is going to rotate. So let us assume that initially the string length is L, which is going to be fixed. So you can say that total length of string is our L, and that is our fixed. And from the top view, we can clearly see that the string is somewhat acting like a tangent. Initially, it is going to act like a tangent. So from here, we can also say that the string is tangent to the post, and for let us call this free length as our L naught. So this is our free length, and this is our R, and the distance of this mass to the center is our small r. So the R is the radius, the string is acting as a tangent, so this angle will be our 90 degree. So from here we can say that the radial distance r from the center. So radial distance, which is of r, will be equal to r square plus L naught square and its square root. And as the mass is going to orbit, so the string is going to wrap. Okay. And so we can find out the wrapped arc length. Suppose it is wrapping around the string. The string is wrapping around the post at an angle of theta. Okay, because it is going to wrap. Therefore, we can say that as mass orbits, the string wraps, increasing the wrapped arc length and that arc length will be equal to our r times theta, and this theta is our wrapped angle in radians. Wrapped angle, and that angle is in radians. So if we look into from the top view, we can see that the string is going to wrap something like this, okay, and it will be overlapping with every circle. Okay, in this way the string will be wrapping, and this is our mass, okay, and the string will be wrapping. And so from here we can find out the decrease in free length let us suppose that if L will be equal to original length minus the wrapped length, okay. And original length is our, which we have called as R, so this R is nothing but our length, which we called as our, L naught. So therefore we can write that our length L will be equal to, this comes as r square minus capital R square square root minus r times theta. And similarly in this case also we can assume any radial distance, that is our rho. Okay. So we can say that for a radial distance which is our rho, then this rho will be equal to our r square plus L square and its square root. And this will be the center, and this circle, overlapping circle, will be all having a radius of r. Therefore we can say that this mass is going to hit the post when our rho becomes equal to r. So it means this radial distance which we assumed, as soon as it becomes equal to our r, this mass is going to hit the post. So first of all, let us once again try to find out what is the conservation of our angular momentum. And like we said, the force of tension will be tangential to the circle. So in this case also the force of tension will be tangential to the circle. Therefore we can say that at any instant the string is straight from the mass m to the tangent point. And therefore the tension force T, therefore we can say our tension T acts along the free string, or we can simply say that the tension T acts along the free string. So now let us find out. Okay, for that this basically means that it is wrapping in this direction, and at particular instant this is a mass m, and we are going to have tension T, and this tension T will be as a tangent to the circle. Okay, this is our radius r. So let us try to find out what will be the angular momentum, whether it will be conserved or not. So for that we have to find out once again the torque about the center O. So we can say that torque about center O and we know that the tension force is tangent to the post and it is perpendicular to our R. Therefore our torque, our tau will be equal to T dot R, okay, which will be not equal to 0. So which basically means that there will be external torque. Okay. And if there is external torque, or we can say external force is acting there, our angular momentum will not be conserved. We can say our angular momentum about point O is not conserved. And our linear momentum will not be conserved, because the tension T is going to generate external force and it is always going to change the velocity. And we can also check our energy conservation. So we have energy conservation, and we know that our tension T and the string, the velocity V is perpendicular to each other. So we know that since tension T and velocity v is perpendicular to it, therefore instantaneous power whichever p, that is t dot v, will be equal to 0. And for the entire motion, we can find out the work done by the tension. So we can say that over entire motion, work done by the tension will be given as the integral t dot ds, and which will be equal to 0. So it means there is no work done on the string. No work done on the string. And so obviously there is no friction, therefore we can say that the kinetic energy will be conserved. So we can say the kinetic energy, which suppose at any point is our half mv square, is conserved. And we can find out also our initial kinetic energy, that our kinetic energy initial is equal to our half m v naught square. So if both are the kinetic energy is conserved, therefore we can write our half m v square is equal to half m v naught square. Here half m cancels out, therefore we get that v is equal to our v naught. So this is our velocity at a distance rho, and because it says that at any point the velocity is v, and v naught is our initial velocity, therefore we can say that our velocity at point r, as it is going to hit the post, will be also equal to our v naught. So we can see that the relationship between the initial velocity and the final velocity in part A and part B is entirely different. Okay, because in part A there is no external agent that is acting as an agent to work, whereas in this case there is, you can say, an external force. Because of that, torque is 0, but the work done is equal to conserved, that is no energy losses. Next question. It states that a pendulum consists of two identical discs, each with mass m and radius r, connected by a massless rod. One of the discs is pivoted at its center using a small pin. The discs remain in the same plane with their centers separated by a distance L. Determine the period of small oscillation of the system. So in this case, we are going to divide the question into two parts. In the first part, we are going to consider that the rod is massless. In the second part, although it is not mentioned in the question, we are going to solve the same question, but we are going to use that the rod is having some kind of mass. Okay. So first of all, let's consider this massless rod, and we can draw an approximate figure for that. So we have two identical discs. Suppose this is a disc which is radius is r and mass is m, and this is pivoted at the center. and to this disc another disc is connected, which is also same, and its r is the radius and m is mass. Okay. And L is the length of the rod that is in between the center. So our this top one disc, let us suppose this is our D1 and this is disc D2. So D1 disc is pivoted at the center. So in this case, we have to find out the time period for small oscillations, and that we know is our standard formula. We are also going to derive that derivation, but let's solve this particular case first of all. So we know that for small oscillation means if theta is this small, so you can say for small oscillation, we can write that the time period t will be equal to 2 pi square root of I. I is our moment of inertia of the entire system about the pivot point. Let us call this a pivot point as P. And we have this as m times g times d. And this d is the distance from the pivot to the center of the mass of the system. Okay, so let me write these two things. First is our I, and this I is our moment of inertia of the system about pivot axis. And we have our d, and that d is our distance from the pivot to the center of mass of the system. Center of mass of the system. Okay. And let us solve the question, then we come to our this derivation. And we are given that rod is massless. Therefore we can say the total mass let us suppose that is our small m will be only the mass of first disc plus mass of the second disc, and that is our 2 times m. And let us assume that the distance, okay, let me draw this figure here, and this is the upper disc, and our lower disc. So this is our D1 and D2, and we assume that the distance between the center of mass, okay, let us suppose the center of mass is somewhere here, is D from the point of pivot P. So we can say, or we can find out that distance to the center of mass and so for this particular case, let me redraw the figure, and because otherwise it will be tricky. So in this case, this is our disc 1 and it is hanging vertically downward exactly. Okay, so this is our D1 and this is our D2. Okay. So the lower disk is exactly in the, you can say, vertically downward, directly below the upper disk. Therefore, we can write that the distance of the center of mass d and this d will be equal to upper mass and 0 multiplied by lower mass and distance L from the point of pivot and summation of both the masses, and this gives us our ml upon twice m, and here m and m cancels out, this giving us L by 2. So this is nothing but a general formula, which in we know that it is equal to summation and the product of our r of I and our m of I, okay, and divided by their summation of the masses. So this is the general formula to find out the distance of our center of mass. Now let's find out the moment of inertia about the pivot I. Moment of inertia I about the pivot. And here we are having, sorry, so here we are having two discs, okay, and one is a upper disc. So let me draw this is our pivot point P. So for upper disc, which is our D1, the pivot point is at a distance r from the pivot. So this is distance r, which is basically radius for our disc D1, and its mass is our m. Therefore, for the upper disc D1, moment of inertia, let us call this as I D1, will be equal to half m r square. Okay. And for the lower disc, so this is our pivot point P, and the lower disc is somewhere here. Its distance is given as r and mass is of m, and it is at a distance of L from the pivot point P. So we can see that first of all we are going to find out the moment of inertia for the lower disc D1 about its center, and then we are going to use parallel axis theorem to find out the moment of inertia about point P. So you can say for lower disc D1, lower disc D2, this is D2. Its moment of inertia about center of mass, which is our ICM, will be equal to half m r square. And second, and then we come to the pivot point P. Okay. So we can say, using parallel axis theorem, we can write that moment of inertia about pivot point P, let us call this as ID2, will be equal to moment of inertia about its center of mass plus mass and the distance square, which is our L square. And we get from here, this will be equal to our half m r square plus ml square. So the rod is massless, so it is not going to contribute any to moment of inertia. Therefore, we can say that our total moment of inertia which we have considered as I will be equal to our moment of inertia of disk 1, moment of inertia of disk 2, and this comes as our half m r square plus half m r square plus ml square. And this half and half is going to give us 1, so this comes as mr square plus ml square. Therefore, we can write that our moment of inertia I, we can take m as common, so this comes as our r square plus L square. Now we can easily use the formula which we just written. That is our time period T will be equal to 2 pi square root of I upon mgd. And we just found out everything, so we substitute it. I was our m r square plus L square, and this is mg, and d is our L by 2. And here, sorry, one thing I missed it, that is mass. Mass is about twice m. So this mass and mass, 2 and 2 cancels out. Therefore, this comes as our r square plus L square multiplied by gl square root and 2 pi. So this is our time period for small oscillations. And if you want to drive, we can also drive this particular relationship. This is quite simple. And so in this case, we usually drive this for a small angle theta, because here we use the approximation that our, let me draw the figure. So here we are having a pendulum, and this is angle of theta, and mass of the rod is suppose mg, so that will be acting at the center of mass in the downward direction, and let us suppose it is at a distance d. Okay. And therefore we can say that for small angle theta, the perpendicular lever arm is approximately d sine of theta. Okay. So we can say that perpendicular lever arm is our d sine of theta, and small angle approximation, this gives us that it is equal to d of theta. And the torque, which is our tau, will be, because it will be restoring torque, so this will be coming as minus mg d sine of theta. Okay. And according to our second law of Newton's second law of rotation, we can say that our second law is also giving us a torque, and torque will be equal to our I and double derivative of theta. Okay. And that will be equal to our minus mg t sine of theta. Okay. and for small angle the sine of theta will be equal to theta. Therefore from here we get that our I double derivative will be equal to our mg d theta is equal to 0, and we can write this as theta double dot will be equal to mg d upon I multiplied by theta is equal to 0. Okay, and this is nothing but our equation of our SHM, and from here we can write that our angular frequency, that is omega square, will be equal to mgt upon I, which gives us that our time period, which is equal to 2 pi upon omega, giving us 2 pi square root of I upon mgd. Okay, that's why the small angle interpretation is very important. So we can just assume that the higher angles can be neglected. Now we come to our second part. In this case, we are going to say that our connecting rod is not massless. Connecting rod is not massless. Okay, and let us suppose it is having a mass of m. So the main contribution or main change in the solving of this particular question will be equal to finding out our moment of inertia. Okay. And the formula of the time period is going to remain same, with the minor addition will be there. So we can say that our time period t will be equal to 2 pi, and this will be the square root I mass of the two disc plus mass of the rod and multiplied by g. Okay, this will be the major difference. Okay, so here the total mass will be our 2m plus small m. Okay, let me write this as capital M. And once again, let us find out the moment of inertia which we are required to find out. So once again we start with our total mass, and the total mass is our m plus capital M plus small m, which gives us 2m plus small m. That is the total mass of the system, which is disc and one rod. Now we are going to find out distance to the center of mass, which is our d, and that is also going to change. Okay. Distance to center of mass, which is our d. And we already know that this is our rod, upper disc, and in this case also we are going to say that it is vertically downward. Upper disc D1, lower disc our D2, and for the rod whose length is of L, for this rod of length L, we are very sure that its center of mass will be lying at a distance of L by 2 from the pivot point. Okay. We already know this because mg will be acting at this particular point in the downward direction. Okay. And once again, for the upper disc, the distance that is our pivot, because the pivot point is itself on the disc, so that distance will be equal to 0. So we get the distance d will be equal to, in the numerator we have total mass m plus small m, and on the upper we are going to have our upper disc multiply with its distance plus lower disk mass, not the rod and its distance, plus the lower disk and its distance. So this gives us the value of D will be equal to, we will get this as ml by 2 plus ml and divided by 2m plus small m. And we can take L as common, so this comes as our m by 2 plus capital M multiplied by L, and this is twice m plus small m. So this is the position of our center of mass. And now we come to our moment of inertia about the pivot point. Moment of inertia, which is once again we are going to say I about pivot. And we are going to consider the individual. First one is upper disk, and upper disk is the pivot point is at a distance r, so its formula is going to remain same. So we can say for disk D1, it will be equal to, let us suppose, ID1, and it is equal to over half m r square. For the lower disk, once again the formula will be same. For disk D2, let us call this as ID2. First of all, we are going to find out with respect to the center, and then we are going to shift it by the our distance, that is mass m, and distance is our L square, and ICM is our half m r square plus ml square. Okay. So this is also going to remain same. The only major change will be for our rod. So we can say for rod, let us call this as IL, and we know that our center of mass is at a distance L by 2 from the point of pivot. Okay. And the, you can say, okay, so let me first of all draw the rod. So we have the rod, its length is L, and we have to find out the moment of inertia at the point which is at the extreme of the rod. Okay, we can write the formula directly, or we can use the standard one. First of all, find out the center of mass, and then we are going to use parallel axis theorem and shift it to point P. Either ways, we are going to get the answer same. Okay. And let us call this as center of mass for rod L, and that we know is our 1 by 12 ml square. So for point P, this will be equal to half ICML plus mass and the distance. Okay. And obviously this will be coming as our one second, this will be L by 2. So let me substitute it. So moment of inertia for the rod about the pivot point will be equal to our 1 by 12 ml square plus this will be our square. So I missed it, that's why. So this will be coming as ml square upon 4. This is small m. ml square upon 4. And this will be 12, 1 plus 3, 3 plus 4. This will be 1 by 3 ml square. So we got our moment of inertia for all the 3 separate identities. Now we can find out our total moment of inertia, which is our I. Total moment of inertia, which is our I, is equal to for disk 1 plus disk 2 plus for the rod of length L. And we can say that our upper I will be equal to half m r square plus 1 by 3 ml square plus half m r square plus ml square. Therefore, we get our I, our mr square half will is going to mr square. So we have this as mr square plus ml square plus 1 by 3 small m l square. Now we simply substitute the values. So we get our time period T will be equal to 2 pi, and in the denominator, that is our total mass, 2m plus small m times g, and we have distance, that is our L, and that is our m by 2 plus m whole divided by 2m plus m. And in the numerator, we are going to get, we have already did, so this is our mr square plus ml square plus 1 by 3 small m ml square and its square root. Okay. And this 2m and 2m is going to cancel out, and rest we can keep as it is, not much difference is there. So T is equal to 2 pi, and we get this as GL small m by 2 plus capital M, and in the numerator we are going to get this as our mr square plus small ml square plus 1 by 3 ml square and its square root. So this is our time period. Okay. And if we require, we can simplify it, otherwise we can keep it as it is, because this is only going to use time. Okay. Next question. It states that a physical pendulum consists of a uniform disk of mass m and radius r suspended from a light rod of negligible mass. The pivot point is located at a distance L from the center of the disk. Determine the value of L that minimizes the period of small oscillation of the pendulum. Okay. So in this case also we are going to solve it two ways. First case, we are going to do it for negligible mass of the rod. In the second case, we are going to consider the rod is having some kind of mass. Okay. And the major difference between this question and previous one, here it is only one disk. Okay. So we have a pivot point, and that pivot point is connected to a disk, and disk is having a mass m and radius is r, and with respect to the vertical, let us suppose small angle is theta, and L is the length of the rod. Okay. So in the downward direction, obviously there will be our mg acting downward, but the method of finding out the time period, the formula will be same. So we can say that time period that is our T is equal to 2 pi square root of I divided by M, G and D. Here m is the total mass of the system, d is the distance of the center of mass from the pivot point, and I is the total moment of inertia of the system. Okay, so these are not going to change. And first of all, let's find out the distance to the center of mass. Distance to the center of mass, which is d. Now the rod is massless, and for the disk the center of mass is exactly going to lie at the center. Therefore we can say that our d is equal to our L. And next is our I is our moment of inertia of the system about the pivot point, and that pivot point is our P. So we have a moment of inertia I about pivot. And once again, first of all, we are going to find out the moment of inertia of the disk, that is d, about its center of mass, and then we are going to use parallel axis theorem to find out about P. So therefore we can write moment of inertia I about the pivot. Sorry, this is pivot. Pivot. And that is our I will be equal to moment of inertia of the disk about its center of mass plus the mass of the disk and the distance, which is of L, so it comes as L square. And for disk we know that it is of half m r square plus ml square. Therefore we simply substitute the values. We get that our time period t is equal to 2 pi, and total mass of the system is of capital M, and d is our L, and numerator comes as half m r square plus ml square and its square root. And this m cancels out, so we get the time period will be equal to about 2 pi and half r square plus L square, and this is our GL and its square root. But in this case we have to find out the value of our length L, which minimizes the time period. So obviously it is talking about the minimization, so we have to differentiate it and substitute equal to 0. That is our minimization, the basic mathematics. So we can say that to minimize t, we minimize because here this 2 pi and g will be constant. Okay. So therefore we have to minimize a function. Let us suppose that function we call this as f of L, and this function f of L will be the function which is our under the square root, that is our L, and this is our half r square plus L square, or we can write this as our half r square L square plus L. So basically we are going to minimize this particular function. Okay. And so that let's find out its derivative. One second, this is not square but L, and we derivate it. Let us suppose this is df upon dl, and that will be equal to over 1 by 2, and this comes as our r square, and this is L square and minus, and this is equal to plus 1. And we are going to equate this term is equal to 0. So we can write this will be giving us our 1 is equal to 1 by 2 r square upon L square, and 2 goes on the other side, therefore we get our L is equal to 1 by square root of 2 times r. So this is our value of L that is going to minimize our time period that was asked. And here, like I said, first case we solved that a rod is negligible mass. In the second case, we are going to consider the rod is having some kind of mass. You can say rod is not massless, and let us suppose its mass is given as small m. So therefore time period formula is going to remain same with the slight modification that will be equal to I, and we have to remember that in the denominator the mass is our total mass of the system, that is capital M plus small m multiplied by G and D. Okay, I is automatically going to change, but the mass of the system is our m plus small m. So you can say that our total mass is our capital M plus small m. Now let's find out our D. That is our distance of center of mass. Distance of center of mass, which we have over D, and this distance is with respect to a pivot point. And so in this case we have our disk D, which is at a distance of L, plus we have a rod of mass M, and its distance is from our L by 2, and giving us m plus small m. And we get from here that our D, L we can take as common, so this comes as L m plus m by 2 divided by m plus small m. So this will be the first change, and second will be change in the moment of inertia. You can say moment of inertia, that is our I, about the pivot. So this is pivot. Yeah, every time I get this spelling wrong. T. So first is for the disk, moment of inertia of the disk will be equal to same moment of inertia about the center of mass plus mass and the distance about the pivot square. ICM we know is our half m r square plus ml square. And now we come for our rod. Moment of inertia of the rod will be equal to, and that is pivoted at one end, so we just found out that is equal to over 1 by 3 ml square. We can just remember the formula also, or we can just drive it. Therefore our total moment of inertia which is our I is equal to disk plus our rod, and disk is our half m r square plus ml square plus 1 by 3, and this is small m l square. And we can just make a minor adjustment here. So we can say our moment of inertia I will be equal to 1 by 2 mr square plus L square we can take as common, and this comes as capital M plus 1 by 3 times small m. Now we simply substitute it into our time period equation. So this is our time period t, that is equal to 2 pi, and in the denominator we have our total mass multiplied by g, and d, that is our distance of our center of mass, and that is our L m plus 1 by 2 m by 2 divided by m plus small m, and in the numerator it is our half m r square plus L square capital M small m by 3 and its square root, and this m plus m cancels out, and we can just keep as it is. There is no need to further solve it. So this comes as 2. Okay, we have to find a minimization. Okay, I forgot it. So this comes as our, let me write it here. So we get our t is equal to 2 pi, and this will be our GL m plus m by 2, and it will be our half m r square plus L square m plus m by 3 and its square root. So once again, that is our two terms, that is 2 pi and g will be constant. So we are going to assume that we are going to minimize a function, that is our f of L, which is our inside the square root, and that comes as our L m plus m by 2, and this comes as our half m r square plus L square m plus, and this is our m by 3. And let us separate them. So we get this as our half m r square, and this will be L m plus m by 2 plus, we get this as our L m plus m by 2 L square m plus m by 3, and this L square goes with L, so it is now quite easy to differentiate it. So we can write, for the sake of simplicity, we can write this as A upon L plus B times L. Okay, and this A is about this particular thing, so this is our A, and our B is this part, because it's not required, we are going to differentiate it with respect to our L. Okay. And so we are going to minimize our f of L, so therefore we can find out its derivative with respect to our L, giving us minus A upon L square plus B is equal to 0, and this gives us that our A upon L square plus is equal to B, and we are interested in our L square is equal to A upon B. Now we can easily substitute our A and B. So we get that our L square will be equal to, A is our half m r square m plus 1 by 2, so this comes as half m r square divided by m plus small m by 2, and our B is our m plus m by 3 and divided by m plus m by 2, and this numerator is going to cancel out, and this comes as our half m r square m plus small m by 3. Okay. And this is almost done. We are interested in length L. So length L, we can solve this if we take 3 as our LCM. So that will be equal to over 3m r square, and this comes as twice, and we have here 3m plus small m, and it's square root. So this is our value of our L, which we are supposed to find out for the minimization of our time period. Okay. So these were the few questions which were based on our conservation and rotation, along with the various theorem. Especially here we did the parallel axis theorem, and we tried to modify the questions as per our, like we took a massless rod, then we solved the same question for the mass rod. Okay, so some minor things were, we changed it. Okay, so this completes all the questions. Thank you.